All right, we're picking up from the last lecture on the Lewis structure for sulfur trioxide. And what we have here again is sulfur trioxide actually has three Lewis structures. We know that this can happen because all three of these structures here, all three of these structures here follow the Lewis structure rules, in that there are a total of 24 electrons here that we calculated previously, and each one of the elements, oxygen and sulfur, have 8 electrons around them. And again, when resonance occurs, the most frequently, or one of the number one indicators that resonance is going to occur is when you can see that a double bond or a triple bond can be moved around the molecule. All right, so I want to develop this out a little further. Let's go to the next page. Now I'm just going to focus on one of the resonance structures for sulfur trioxide. So let's just make it nice and symmetrical. I'll put the double bond on this oxygen and single bonds on the other oxygens. All right, so here we have sulfur trioxide. And the next thing I want you to be able to do with this sulfur trioxide is determine what type of bond is occurring between the sulfur and oxygen. Now we know this is a double bond, a single bond between the sulfur and oxygen on the left and right, and that means one shared pair. And these are the weakest and longest of the covalent bonds. And then in the middle here, the sulfur-oxygen bond, it's a double bond here. That means there are a total of 4 shared electrons. 4 shared electrons. And it is shorter and stronger than the single bonds. All right. The next thing I want you to be able to do is determine what type of covalent bond is occurring between the sulfur and the oxygens. Is it pure covalent, which we just call covalent? Is it polar covalent, or is that ionic? Now we know it's not ionic because ionic requires true electron separation between the elements, and that would be like between a metal and a nonmetal. Because these are two nonmetals, sulfur and oxygen, we know that it's some type of covalent bond. Whether it's covalent or polar covalent, that's what we need to figure out. So how do we figure that out? Well, we look at the electronegativities of these elements, sulfur and oxygen, and we find on the electronegativity table that sulfur is 2.5 and oxygen is 3.5. These are the electronegativities of sulfur and oxygen. Now, if we subtract 3.5 or 2.5 from 3.5, we get 1.0. If the electronegativity difference, which I'll call chi here, is between 0 and 2.1, we have what we call a polar covalent bond. If the difference is 0, it's just purely covalent. And if the difference is greater than 2.1, greater than or equal to 2.1, then we have an ionic bond. This is all about, if you want to look at this in the book, it's under electronegativity. All right, so I'm not interested. If you said 3.5 minus 2.5 and you got a negative 1.0, that's fine. We're just looking at the absolute value here. The difference is 1.0, which means we have a polar covalent bond. So this is a polar covalent bond, this is a polar covalent bond, this is a polar covalent bond. Now, how do we show that in the Lewis structure? We put a partially negative, this is a lowercase delta, Greek symbol delta. You probably know the uppercase delta looks like this, or lowercase delta looks like that. So we put a partially negative on each one of the oxygens because it is more electronegative, and we put a partially positive on the sulfur. All right, and so anytime you see partially negatives and partially positives, you know we're dealing with a polar covalent bond. Now, Why is this so important? Well, when we look at the type of bonding that occurs and the geometry of the molecule, we can determine whether the molecule is polar or not. So let's do this. Let's redraw this. And I just want to ask you this question. If you have three things coming off the central atom, these three oxygens, and you know that the electrons between the sulfur and oxygen repel each other, like charges repel each other, how do you keep three things as far away from each other as possible in relation to the central atom sulfur? How do you keep three things as far away from each other as possible? You should be thinking triangle. There's an oxygen in this corner, oxygen in this corner, and oxygen in this corner. And the degrees here is 120. Because 360 makes a full circle, right? Alright, and we know that this is partially negative, and partially negative, and this is partially positive. So, that is the correct molecular geometry for sulfur trioxide. We call this trigonal because it's like a triangle. This is just an adjective here. Planar because it's flat. Alright, so what theory do we use to come up with this? You came up with it by just thinking about it, right? That how do you keep three things as far away from each other as possible? Well, there's a theory based on this. It's called valence shell. That means outer shell electrons, right? Electron repulsion theory. And what valence shell electron repulsion theory says is that a non-bonding electron interacting with another non-bonding electrons is the most repulsive. Then non-bonding with bonding is the next, and then bonding with bonding is the least of these three. All right, so what we do is this. We focus on the central atom only. We look at what's coming off of the central atom. And in valence shell electron pair repulsion theory, we don't distinguish between the double bond and the single bonds. We count these all as one thing. So we would say there are three bonding pairs coming off the central atom, although this is actually another bonding pair. But again, valence shell electron pair repulsion theory doesn't distinguish between a single bond and a double bond. So we classify this as AX3. Now you go, what does this mean? A stands for the central atom, and the X3 represents the bonding electrons coming off the central atom. Again, no distinguishing between double and single. So knowing that this is called the classification, the book doesn't really talk about this, but I find it very helpful in determining geometry. So if it's AX3, the next question is, how do you keep three things as far away from each other as possible? And that is by placing them in the corners of the triangle. So that's how we determine the geometry. AX3, keep three things as far away from each other as possible, corners of the triangle. In the next lecture, we'll pick up a few more of these. Ultimately, what we're trying to figure out, though, does the molecule itself have a positive or negative end to it? Is there any way you can slice this molecule in half, or at least just run a line through it, like so, and it be strictly negative on one side and strictly positive on the other side? In this case, not. There's no way you can draw a line through this and it be strictly negative on one side of the line and strictly positive on the other side of the line. Because you cannot get a strictly positive and negative side to this molecule is nonpolar. Now, don't confuse this with polar covalent bond. When we say a molecule is nonpolar, we're saying the entire molecule itself does not have a positive and negative end to it. And why is that so important? Because nonpolar liquids or nonpolar substances will not dissolve in water, which is a polar substance. So in the next lecture, we'll do the Lewis structure for water, and we'll develop out the geometry and so forth, and I'll show you the difference.